Welcome to the introduction to inverted microscopes. So we have an inverted microscope here, and we will be talking about how it works and how it's different from an upright microscope, and we'll also be going in detail over the correct cleaning of objectives on an inverted microscope. So we'll take the dust cover off. And we'll have a quick look at what we've got here. Obviously we have the stage. Here's the flat part where we lay our samples. We call the rest the stand. The bit over the top is called the arm, and we have oculars at the front, or eyepieces, and we have a camera port. And so in the current situation we have to protect ourselves and other users from any accidental contamination. The way to do that is we take some cling film to put over the oculars, and we clean the microscope touchable surfaces with isopropanol each time we finish using it. Okay, so as obviously it looks quite different from an upright microscope. The optical principles are much the same, that there's a few more items in the path, so that instead of looking down on top of the sample, we look up from underneath. The reasons for doing this is that we now, with this arrangement, we have easy access to the top of samples, and it also provides a slightly more stable platform than a typical upright microscope, because the stage itself doesn't move, instead the objectives move. Some upright microscopes also are beginning to have this, but it's slightly less common, and it's still slightly less stable because there's a little bit less support for the stage. Okay, so the key thing we need to do when we're taking an image of a sample is we need to get light in and we need to get light out. And this microscope works in two ways. It works with transmitted light, and it works with fluorescent light. And so firstly, with the transmitted light path. At the top, attached to the arm, there is a halogen lamp, a bright lamp. There is a slider for some filters to change the brightness or change the color. And below that, there's the condenser. The condenser contains a number of lenses to focus the light down onto the sample. It also has a slider. This slider will vary what is on this slider on different microscopes. This particular one has some structured light, so to change the pattern of the light that goes onto the sample. In this case, it's for a process called phase contrast. We won't get into that in any detail. Below the condenser, on the stage, we have a sample holder, which we'll look at in more detail, and then we have the stage itself. Underneath the stage, you can see a set of objectives on a turret. The turret rotates round to bring the different objectives to underneath the sample. Below that, there's a filter box, which we'll get into when we discuss fluorescence. And then at the very bottom, there is a mirror, a switchable mirror, or a prism in this case, for a higher light efficiency, which directs the light either up to the oculars or out to the camera port. With fluorescent light, the light goes in a slightly different route. It starts at the back in this box here. At the moment, unfortunately, we need a new bulb in this, so we can't demonstrate the use at the moment. So the ultraviolet light comes in through the back of the microscope and into the filter cubes. We'll look at the filter cubes when we have a look at the controls on the other side of the microscope, because we can't access them from this side. Inside the filter cubes, there are some wavelength selecting filters, which select a specific wavelength up through the objective into your sample. Where it's absorbed, it loses a little bit of energy and is re-emitted at a different wavelength. So when it comes back down, the wavelength filters act differently and direct the emitted light from your sample up and through the oculars or to the camera port. I'm just going to move the camera and we will focus in on the controls that we have available. On the left hand side of the microscope we have the stage control, and you can see as we turn the top dial it moves the stage in the Y direction, and if we move the bottom one we move it in the X direction. You can also see there are some calibrations along here. On this particular microscope the stage only moves the sample holder. You can see the hole in the middle does not move. That makes this a slightly safer microscope to learn on, because there is a smaller chance of bumping anything into the objectives. On our other microscopes there is a lot. The stage moves the hole horizontally. The hole does move with the stage, and you run the risk of bumping the stage or the slide holder into the objective, so you have to be particularly careful with that. We'll discuss that again later. Many microscopes have changeable inserts or slide holders. This particular one has an insert that is designed to take slides, or you can squeeze it close together and it can take dishes. The reason that we have changeable, even though they're adaptable, is that this one can't be adapted to take plates, for example, or dishes of a different size without an insert. So often this part is changeable. Below the X stage control dials we have the focus wheel, and use the focus wheel we have the coarse on the outer, much like most microscopes, and the fine on the inner. The thing that does vary between microscopes is which direction you turn these to move the objective closer and further from the sample. So when you're on a new microscope, check exactly what you're doing, what moves in what direction, to avoid searching continuously in the wrong direction for focus and crashing the objective into your sample, potentially damaging your sample and potentially damaging the objective. And now we'll look on the other side of the microscope. On the right hand side of the microscope we have a repeat of the focus wheel, and we have the lamp controls. So the dial here changes the brightness of the lamp and the switch turns it on, so we'll turn it on now. And you might just about be able to see at the top here a little bit of light, just at the very top of the image. And we have the UV light path control. So we can move different filters in and out to change the brightness of the UV light. And there is a shutter which is in, so stopping the light, and out, allowing the light through. There are also two dials for aligning the light path. As we mentioned before, the UV light comes in from the back through the filters and shutter into the filter cubes. So the filter cubes, as I mentioned before, are to allow us to select different wavelengths of light to run through. This system has 3 holes. One of them is left blank in order to allow non-UV, non-fluorescence imaging. The other 2 have filter cubes in, which you should just about be able to see, have a slanted mirror, which is wavelength dependent and reflects one and allows the other to pass. So you can see from the way it's slanted that the light can come in here, and then goes up like that, and the light that comes back, because it's a different wavelength, goes all the way through. There are also what are called blocking filters, which pre-filter the light before it gets to the wavelength selector, and there is also another filter at the bottom which prevents any unwanted light getting into the eyepieces. I'll slide that back into place. A lot of microscope equipment has very nice springs which click into place when things are in the right position. Okay. See? There's also a light path switch. This moves a mirror within the microscope, and you can hear it click to change the light going to the camera port at the front or the eyepieces at the front at the top. Okay, so we've looked at the various controls of the microscope, and now we need to actually put a sample on. We'll have a quick discussion of objectives. You can see at the moment we have a low magnification objective. This is usually obvious because the lens is very big. So this is I think a 4 times objective, and we rotate the turret so we can reach underneath the stage. There's a roughened part on the turret where we can hold it, and we can just turn it round to bring the next objective into position. And this is a 10 times objective, which has a much smaller pupil. And then as we come around, we're now on a 100 times objective. Now this is an oil immersion objective. The other two are intended to work with air and should never have oil on them because they're not designed to have oil and it can damage them. And any oil on these will ruin image quality, and it will take a lot of work to get them cleaned, meaning the microscope goes out of action. Obviously, looking at these as I rotate them round, they are different distances from where the sample goes. And this distance here is called the working distance. The closer the working distance, typically, the higher the quality of the image you can obtain. And so the 100 times objective, the oil immersion objective, it's very close to the sample and can obtain the higher quality images. Of course, this comes at the cost that you run the risk of scraping the objective against the sample or against any part of the microscope which is at about the sample position. So bear that in mind and be especially careful with the short working distances and high magnification objectives. They are usually spring loaded. As you can see, I can push this down and a spring does move down. This only protects the objective during focusing. Moving side to side, it's not protected because the spring is obviously vertical, not horizontal. We will now go back to a low magnification objective because when we need to focus something, we almost always start with a low magnification objective and then switch up. So I have a sample here. It's a sheet of fluorescent paper. It being an inverted microscope, we have to invert the sample as well. So we take our sample, we turn it over so that the cover slip is down, and we insert it into the holder. Now there are different types of holders on different microscopes. This type of sliding holder, you hold the slide, you pull it apart, and then you lower the slide in and you push the holder closed, and it holds it because the edges are beveled so that the sample is held in position. Some stages have metallic clips instead which hold the slide down. And we would do a similar thing if we were dropping in a dish. We would make sure that the spacing is about right for the dish. We'd drop the disc in when you push these in sideways so it's held as securely as possible. In some circumstances it's not so easy to hold things securely. Often a little bit of blue tack can help, but nothing more permanent than that. Okay, so I'll just centralize so we have see the light hopefully is pointing right at the middle of the image. of the sample, and then we'll bring the focus up while looking in the oculus. If you don't see anything, check the light path. Check that the switch is in the right position. And that the filters are in the right position for what you're looking at. So if you're looking at visible light, you don't want a filter in the way. And if you're looking at UV, you want to be sure that you have the right filter for your fluorophore in position. So I have that in focus now. You'll have to trust me because we don't have a camera on this microscope at the moment. And so that's at 10 times. I have a very wide field of view with this. On the condenser. Okay, so we're in focus at 4 times. Obviously 4 times isn't a great deal of magnification, so we rotate the turret around to the 10 times objective. Because both the 10 and the 4 times objectives are air objectives, so there is no immersion media, we can just do that, and then we can just change it round, and then we may have to fine-tune the focus, because not all objectives have exactly the same perfect focus point. It's better on more expensive microscopes with more expensive objectives. It's actually not too bad on this one. We can't do this, we can't continue this with the oil objective, because if we rotate it round, we still need to get oil between the sample and the objective. And so we'll now, to do that, we have to take the slide off. And rotate around. Now there are a number of other ways we can do this. What we'll start with the most simple method first. So now we have our oil objective in position. We need to put some oil on there, and so the method to put it on is you'll have an oil bottle similar to this on most microscopes. Some have a squeezy bottle instead, but which I actually am less keen on. But they have a dipstick inside. So the dipstick looks like that. And we want just enough oil on that when held horizontally, it doesn't drip. And we take that drip and we allow the drip, but not the stick, to touch the top of the objective. And you can see we now have some oil on the top of the objective, and before it all flows away, we put the slide on again and push it in so it's held steadily. And now it's held in place by surface tension. And now we return to the oculus, look down, and fine-tune the focus. You won't need to move it much. You will just be able to get away with turning the fine focus on this microscope, because it's fairly well aligned. So let's say we take our images, we want to change our sample. So we now have to take the slide off again. But first we take a bit of lens cleaning tissue. Other brands are available, but this is the one we use. And holding the lens tissue, we fold it over once and we hold it at the edges. Now on many inverted microscopes the arm would move back to give us a bit more space, but on this one it doesn't. But we loosen the slide in the slide holder, we pick the slide up, we put it down the right way up so the oil doesn't go everywhere, and we hold holding the lens tissue tight, like so. We wipe it across the top of the objective. And so you should do this every time you change the slide and every time you change the objective, until it comes across clean. can see there's a small amount of oil on the first bit of this lens tissue. And we put the lens tissue aside somewhere where it won't get dust on it, because we'll need it again later. And I will just go and clean the slide so we can then demonstrate other techniques. Okay, so when using fixed specimens like this one, some people find it easier to take, again, the same amount of oil, just enough that won't drip off by itself, and they put it on the slide instead of the objective. So we've got a little drip on the middle of the slide, flip it over and lower it down onto the objective, and then you can see we have that is now again held by surface tension. So that is another way that you can put the oil onto between the objective and the sample. So you can apply it to the objective directly, you can apply it to the sample directly. And we will bring that out again. These oils they're specific to the objectives that you're using. They're similar, but they can be different enough that you can run into problems if you mix them. So it is important that you clean your slides if you're using them after you use them. Isopropanol is a pretty good solvent. If it doesn't work, ethanol also is good. Anyway, so we've taken the slide off again. We need to clean the objective again, so we take our bit of lens tissue, we fold it over until we've got a clean bit, hold it tight at the edges, and rub it gently on the top of the objective. Never applying direct pressure where the iris of the objective is. Always applying tension to the tissue and allowing that to pass the pressure through. And the reason being, you don't want to put too much pressure on the glass on the objective, and you also don't want to run the risk of grease from your fingers getting onto the objective and contaminating it. Okay, another technique. So, for example, you're working with dishes, live cells in a dish or in a plate, and you focused using the lower magnification objectives. And you don't want to lose that focus and your position while putting the oil in. So this is a little bit more of an advanced technique, and it's so on a motorized microscope, like most confocals, they have the ability to set position bookmarks. So you would tell the computer, the software and the computer, to save the position that you're currently looking at. And then you would, instead of taking the slide off to get access to the top of the objective, you move the stage out so that you have access to the top of the objective. Then you rotate the turret or change the objective in software, which rotates the turret for you on the motorized microscope. And we do the same trick as before. We apply oil as before. Again, just enough that it doesn't drip when held horizontally, and just let that drop down by surface tension. We don't touch the stick to the objective, we just let the droplet touch by surface tension. And then we tell the software to move the sample back, across, and it stays in focus. Now, there are some restrictions to when you can do this, because you'll remember that we have a very, very small distance, like 0.2 millimeters in some cases, between the end of the objective and the top of the cover slip. So if you have applied, for example, nail polish around the side of your sample to seal it, that could very easily be too thick, and you'll scrape the nail polish across the top of the objective, contaminating it, damaging it, and needing it, and it will have to be replaced. And these things cost as much as a small car. So I would say you would only use this in the situations where you're using specially prepared tissue culture dishes or plates, or you are not using any sealant around the edge of your cover slip. So it can be used if necessary, but it has to be used with care. So we'll now take our sample off again, put it aside, clean the objective for one last time. So we're folding the lens tissue over until we have a clean section, holding it tight, rubbing it across the top of the objective until it's clean. And now we're done. We'll move to a position where there is no objective to keep dust off the objectives. Turn the light off, and then remove the cling film from the oculars and put the cover on to keep the dust off. On this particular microscope you have to move the stage across, otherwise there's a metal bar that sticks out.